All right. Good morning again, everyone. And thank you for joining me today, albeit the very late notice. Kasi I remember last week I mentioned that we can take Wednesday off yung ngayon. Wala sana tayong lecture para mabigyan kayo ng time para matapos yung laboratory exercise 4.1 na ngayon ay ginawa ko na lang lab exer 4. Pero para mas okay na mag-meet tayo today because there's actually almost a 95% chance that I won't be able to finish everything that I want to say in Module 9 today. In fact, hindi ko pa nga natapos isulat yung buong Module 9. So ito pa lang yung kalahati, which I think is sufficient for today's lecture. So we might need to meet on Friday. Pero alam ko merong request from the USC to the Chancellor requesting the cancellation of synchronous classes on Friday to give students time to travel back to their localities kung saan sila boboto. So there is a chance na mawalan ng synchronous classes on Friday. So mas okay na mag-meet na tayo ngayon. And then whatever will not finish, ay siguro i-record ko na lang. Gawa na lang ako ng recording. Siguro gawin ko rin on Friday para kung may klase man or wala on Friday, doon ko gagawin yung recording. I'll make it available to you before the weekend so that while you're traveling, you are on the bus or come Monday when you are exercising your solemn privilege and civic responsibility of voting, ay pwede nyo mapanood habang nakapila kayo sa polling place, na-download nyo na yung video so you can watch it. And just to complete my thoughts about about Unit 2, because essentially Module 9 is the culmination of our journey along the numerical methods for solving linear equations. So, ibig sabihin, tapos na yung Unit 2, so we can have problem set number 2, which will cover essentially Unit 2 of the course. Kailan kaya natin to gagawin? Yung 155, ibibigay ko yung problem set nila on Friday, and it will be due Friday next week. So, will it be okay, guys, if I give you our problem set on siguro next Wednesday? Tapos ang deadline niya ay Wednesday week after next. So let me see what are those dates. Okay, so I'm proposing I release the questions for problem set number 2 on May 11. So PS2 release. Sulat ko na rin kasi makakalimutan ko ito definitely. So my proposal is to do it on May 11. And then the deadline would be, there would be 3 items or 3 numbered items. So essentially, at least a working day per item. Pero siguro kung 11, 1, 2, 3, 4, 5. Sige, gawin na nating May 18 yung deadline. Is that fine with you guys? Same format as last semester? Last semester, sorry. As the problem set number 1. Ang dami na nangyari. Last semester na ako, no? Parang, di pa ba tapos yung semestre? Pero anyway, any objections with that timeline? Medyo may overlap to na isa or dalawang araw with the 155 pips, but I hope that's fine. Kasi the last day of classes is on June 9, so I think we just have a month left and we still have a unit to cover. So wala tayong pahinga starting next week on the 11th. We will be discussing numerical methods for ordinary differential equations. So we'll have 4 weeks to do it. Medyo tight yung schedule na natin. But we can do that, all right? So yung mga mainstays natin sa chat, mukhang wala naman mga objections. How about the others? How are you feeling about it? Or neutral kayo? Okay lang maging neutral sa discussions natin, pero sa election huwag kayo magiging neutral. Vote kung sino man yung gusto nyong iboto. But hopefully, you did your homework, you did your research. Kung sa paggagawa ng lab exer ay nag-prepare kayo, sana para rin sa Lunes. Anyway, let's not talk too much about that. Medyo triggering yung topic, especially when I open my Facebook pagkagising ko kanina mga 10 a.m. ay parang triggered kagad. So, wag na lang. Okay, hold on. Okay, so another thing that I changed in our class policies ay yung lab exer 4.1. It was supposed to be exer 4.1 worth 35 points. Tapos meron sanang second part ng lab exer 4 which will cover the things that we'll talk about in module number 9. But I decided last Monday na wag nila magpa-exer about module number 9 para yung ipaggagawa niyo sana ng lab exer 4.2 ay ipang-research niyo na lang kung sino yung dapat yung mga iboto. Ano? So, gagawin ko na lang 50 points yung lab exer 4. So anyway, you still have until Friday to do it. Pag nag-declare ng suspension ng requirements, pag may lumabas na memo, pag pinagbawal na kami ay magpa-submit ng mga requirements on Friday, i-move natin ito to Tuesday. So medyo talaga mahaba pa yung mga araw na mahaba pa yung panahon niyo para tapusin ito. But hold on, I see CK's suggestion 10. Ano yung ano yung 10 CK? May 10 ba? Gusto niyo na ng lab X? Gusto niyo na ng ano? Gusto niyo na ng problem set?
Hindi, sir. Presidential bet po yun. Sorry.
Okay. So, yeah. All right. Hindi ako pwede magkomento about that civil service rules. But anyway, so yon. Okay, push tayo doon. Siguro, let me see a show of hands. Sino dito yung kailangan bumiyahe sa Friday? Meron ba? Yan yung inisip ko eh. Baka naman lahat tayo ay naka-work from home naman so hindi nyo kailangan bumiyahe. Sige, so antayin na lang natin yung announcement ng USC. Pero I hope you started doing it. Madali lang naman siya. Actually, I hope you realize na simple lang yung code. Medyo I don't know, pero feeling ko talaga straightforward siya. And hopefully D2L peeps already seen this because I shared my code. It's a very simple code, so I know you guys can do it. Okay, so for this module, I'll just share to you some of my concluding thoughts about solving linear systems. Because basically the methods that we talk about, those are direct methods, which are the factorization methods. We have the LU factorization, kahit yung usual Gauss-Jordan, they work for special kind of matrices. Unang-una, dapat yung matrix ay invertible. Okay, or non-singular siya. Dapat may inverse siya to guarantee the existence of a unique solution. And the number two, dapat or consequently, siya dapat ay square matrix. Kasi walang konsepto ng inverse para sa mga matrices na hindi square. Kasi for a matrix to be invertible, they should exist a matrix A inverse such that A inverse times A is equal to A times A inverse equals the identity matrix of the right size. And remember, matrix multiplication is very picky insofar as the dimensions of the matrix being multiplied are concerned. So dapat nagmamatch yung number of column nung left multiplier yun sa number of rows nung right multiplier. Kailangan nagko-commute yung A at saka yung A inverse. So ibig sabihin, dapat pareha sila ng dimensions. So if this is n by n, or this is necessarily an n by n. The number of rows must be equal to the number of columns. But the question is, sir, paano na kapag meron tayong mga matrices na hindi square or they are rectangular in nature? So that is, we have matrices that are m by n with real or complex entries. So paano natin isosolve yung mga linear systems na yon? But basically, before you go there, we ask ourselves, relevant ba na pag-usapan pa yung pag-solve ng mga systems of equations na hindi naman square yung coefficient matrix, all right? Now, apparently, it does. It is very relevant, especially for applications. Kasi sa applications, maraming mga natural and physical phenomena meron mga models na na-reduce into a rectangular system of equations. Either it is an overdetermined or an underdetermined system, which I will flash later kung ano yung ibig sabihin ng mga systems na to. Ganun din yung nangyayari para dun sa mga iterative techniques na kinonsider natin. Because remember, sa iterative techniques, kailangan ay hindi lamang non-singular yung requirement kay matrix A. Actually, mas maarte tayo dun sa splitting methods na diniscuss natin kasi nire-require natin na yung coefficient matrix ay hindi lamang invertible para sa iterative techniques, pero dapat wala silang wala silang zero diagonal entries. Okay? Kasi pag nagkaroon ka ng zero sa diagonal, yung matrix D, yung diagonal part niya ay hindi na magiging invertible, hindi niya na ma-define yung iteration matrix para sa Jacobi, sa Gauss-Seidel, at saka sa SOR method. Okay? So, kaya medyo limitado yung mga techniques na diniscuss natin, tapos hindi siya magiging enough kasi baka along the way you will encounter non-square matrices. And that's the objective of this module. So, titingnan natin ano yung mga paraan para mag-solve ng mga non-rectangular matrices at saka sa mga matrices na ill-behave o ill-conditioned. Na pagka binago lang natin ng kaunti yung right-hand side, then mababago na completely yung solution na makukuha natin. Meaning, a small change in the input will result to a very big or significant change in the output. Yun yung ayaw nating mangyari. Kasi nga sa physical phenomenon, usually yung right-hand side siya ay measurements. And measurements are prone to errors. May margin of error yan palagi para mga surveys lamang. So, pag walang perfect measuring device. So, pag kumuha ka ng measurements, yun yung ginawa mong right-hand side ng iyong equation AX equals B. Pag nagkamali ka ng konti, o kung medyo off yung measuring device mo, posibleng mali na yung solution na makuha mo. So how do we guard against those scenarios, even if our matrices are ill-conditioned or ill-behaved, that a small change in the input will result into catastrophic changes in the output? Okay? So yung titingnan natin ngayon. Oh, by the way, before I forget, please download the latest version of module number 8. May mga corrections akong nakita when we are discussing the remaining portions of it last Monday. Tapos yung lab instructors, meron din silang mga napansin na corrections. So paki-download siya, and then what I did is I highlighted those corrections that I made kagabi by yellow. So yung mga yellow na makikita nyo dyan, yan yung mga corrections na binago ko. So take note of those. Burahin nyo na yung luma para walang ebidensya ng mga typo errors ko. Alright? So isipin niyo na lang kayo yung proofreaders ko or copy readers ko para sa modules, Para next semester or next year kung ako man na magtuturo uli, almost perfect na or at least better na yung modules. At hopefully naka-latex na rin siya, Okay. All right. So yeah, let's move forward and look at ways on how to solve rectangular systems. Okay. Hold on, guys. Okay. Now, I started here by saying na hindi lahat ng mga linear systems ay n by n or nagre-result sa isang coefficient matrix na n by n. There are what we call underdetermined and overdetermined systems. When we say actually, yun lang yung sinabi ko dun sa first page. So, punta na tayo sa next page. Meron tayong tinatawag na underdetermined systems. Ito yung mga systems kung saan ang number of equations ay mas kakaunti sa number of, underdetermined siya kapag mas kakaunti ang equations kesa sa unknowns. Because you can think of it this way. Yung mga equations, sila yung isipin yung constraints. Sila kasi dapat yung mga ma-satisfy ng ating variables. And then you can think of the variables as our degrees of freedom. Ito yung free tayo kung pumili ano man yung mga values nila. So yun yung mga x's, yung mga posible nating degrees of freedom. So if you're solving ax equals b, the vector x contains the degrees of freedom. Kasi yun yung mga values na pwede nating i-treat as an input para dun sa modeling natin, right? Sila yung nababago. Sila yung pwede nating bigyan ng value. May freedom tayo to choose what those x values are or what are the entries of the vector x. yung equation, sila yung nagsasabi paano natin dapat piliin yung mga degrees of freedoms. Degrees of freedom. So sila yung mga constraints, or they are the checks on the values of the x's. All right? So kapag ka mas kakaunti yung equations, ibig sabihin kokonti yung conditions na kailangang masatisfy ng mga degrees of freedom. So kapag ka you have less constraints than the number of degrees of freedom, what you get is an underdetermined system. All right? So mas marami yung variables, mas marami kang freedom kaysa dun sa mga constraints na nangyayari. All right? So one example is this. This is an underdetermined system. Kasi meron ka lang dalawang equations, because remember in a coefficient matrix, the number of rows represents the number of equations in your system, and the number of columns refer to the number of variables in the problem, or the number of degrees of freedom. So here we have two constraints or two equations, but we have 3 degrees of freedom. Mas marami kang freedom kaysa sa constraint, so underdetermined to. Kulang yung mga rules to get a unique solution. All right? So that means, yes, underdetermined to, tas may dalawa pang scenarios. Pag meron kang underdetermined system, pwede siyang maging consistent, meaning there would be a solution, or it could be inconsistent, wherein there will be no solution at all. So for instance, this first equation you see here is an underdetermined system, but it doesn't have any solution. Okay? Kasi kung meron siyang solution na x1, x2, x3, the first constraint will tell us that x1 plus x2 plus x3 equals 1, but the second constraint will tell us that x1 plus x2 plus x3 must be equal to 0. So those two equations or constraints are contradictory to each other. So wala talagang vector x na makakasatisfy ng underdetermined system ito. So this is what we call an inconsistent linear system. There would be no solution at all. All right. However, the other equation that I have here is consistent. Okay? Kahit siya ay underdetermined. Kung siya ay consistent, ibig sabihin meron siyang solution. All right? So in particular, solution niya si what? Si negative yung nga ba solution to? For instance, si negative 3 halves, negative 3 halves, 1 half, comma 2. Silang yung tatlong numbers na yon could be the entries of the vector x, and you'll get an identity. So magiging true yung equation, right? But under determined systems, kung meron silang solution, hindi unique yung solution na yon. Di siya katulad ng mga singular mga non-singular equations kung saan unique yung nakukuha nating solution. For underdetermined systems, if there exists one solution, there will be an infinity of solutions. All right, there will be an infinitude or a family or an infinite family of solutions. For instance, in this underdetermined system, ito yung form ng mga solution. There's a free variable. Pwede kang pumili ng kung ano naman si x2 ang gusto mo. And once you get an x2, you can compute the associated first component or first entry for the vector x. Yung third entry ay fixed na 2. So, yun yung family of solution para dito sa underdetermined system ito. So, if we have an underdetermined system, either it's inconsistent, meaning it doesn't have any solution, or it is consistent, it admits an infinitude of solutions. Okay? Tapos may isa pang klase ng rectangular system, sila naman yung tinatawag natin na overdetermined. Siya naman yung complete opposite ng underdetermined. Mas marami yung constraints kaysa sa degrees of freedom. Okay? So you have more equations to be satisfied than the degrees of freedom. And an overdetermined system can either be inconsistent or consistent in the same way as underdetermined systems. Kaya lang most interesting overdetermined systems ay madalas inconsistent, especially yung mga lumalabas what do you call this? Lumalabas sa mga inverse problems, which I will siguro talk about after we discuss the Moore-Penrose Pseudoinverse. And that reminds me, shameless plug na guys. If you're interested to know more about the mathematical aspects of inverse problems like paano, ano ba example ng inverse problems? Paano gumagana yung X-rays? Or paano gumagana, paano gumagana? Paano tayo nakakakuha ng picture ng ating internal structures using X-ray? Alright, kasi ang ginagawa ng X-ray, meron ka lang mga, gumagamit siya ng X-ray, binobombard yung katawan mo, tas may film na nakasalop para dun sa remnants ng X-ray na dumaraan dun sa katawan mo, right? The intensity of the remainder nung X-ray na na-capture ng film, yun yung ginagamit ng mga medical technologists to reconstruct a picture of your internal organs, all right? So yun yung parang tinatawag natin na non-destructive imaging or exploration. So isa siyang example ng inverse problem wherein you have the output, which is the data coming from the film, all right? Tapos ang gusto natin ay sagutin yung inverse problem, which is ano yung dinaanan ng X-rays para makuha yung data na yon. So if you're interested with that and you still have some free major electives, you can take my course on the computational aspects of inverse problems na hopefully ma-offer as a Math 191 this coming first semester. Ano? So sorry, shameless plug, hindi ko lang mapigilan. So if you guys are interested, yeah, you can enroll in that course. But anyway, so tingnan natin, paano tayo nagsasolve ng over or underdetermined system? Of course, hindi nagagana yung LU factorization natin from last time, the way it was presented, but I'm sure there are modifications to it to allow for rectangular matrices. Pero kahit doon, maraming requirements para dun sa rectangular matrices. At hindi na rin gagana yung iterative methods the way we described it before, kasi yung splitting methods na diniscuss natin under our iterative section ay nagre-require ng diagonal decomposition or diagonal part, which should be invertible. So in the case of rectangular systems, hindi natin pwedeng magamit without substantial modifications yung mga previous methods na diniscuss natin. So I will discuss today one of the most generic and straightforward way of solving rectangular systems, and that is what we call the Moore-Penrose Pseudoinverse. Okay? So yung pseudo-inverse ay isa lamang attempt to generalizing the concept of matrix inverses to admit the class of rectangular matrices. So tinatry nating palawakin yung definition ng inverse. At ang pinaka-widely accepted notion of the pseudo-inverse ay yung pinropose independently ni Eliakim Hastings, Arne Bierhamar, and Roger Penrose. I'm not sure about the history kung bakit nawala sa billing si Bierhamar, but I guess it's medyo mahirap kasing banggitin yung kanyang apelido. So I will use Moore-Penrose na lang. After all, that's the popular name for the pseudo-inverse, right? Makikita nyo, amazing, no? Kasi kahit magkakalayo yung time span before they proposed the concept of the pseudo-inverse, they are all credited for it kasi independent nilang na-discover yung konsepto ng pseudo-inverse. Moore did this work in 1920, Bierhamar in 1951, and Penrose in 1955. So, pero independent yung pagkaka-discover nila, so they should all be credited for this concept of the pseudo-inverse. So, paano nila generalize yung konsepto ng inverse? So, ang ginawa nila, define nila yung pseudo-inverse for all complex matrices. Alright? So, wala nang condition na mapa-square man yan, mapa-invertible man yan, may properties ba yun na satisfy? Hindi. Ang goal kasi nila sa pseudo-inverse, lahat dapat ng matrices magka-pseudo-inverse. Okay? So, kung meron kang matrix A, some linear algebra terminologies muna. If you have a matrix A that is m by n, tas meron siyang complex entries, okay? So yung transpose ng matrix, I know we used it before, is denoted by A upper T, A upper capital T. So siya yung matrix na pinagbaligtad natin yung row at saka column number. So if a number resides in the ith row and jth column of a matrix A, then the same number will be on the jth row and ith column of its transpose. So yun yung transposition ng isang matrix. While there is a concept of conjugate transpose, pag complex yung entries ng matrix. Now, if you have complex entries, yung conjugate transpose, which is denoted by A star, siya naman yung matrix na ang laman niya ay yung, or actually, siya yung transpose ng matrix A, pero after transposition, kukunin natin yung conjugate ng mga complex entries. Remember, if you have a number A plus BI, ang kanyang conjugate, ang notation natin sa conjugate, lalagyan lang natin ng bar, yung complex number sa ibabaw. Ito ay equal lamang sa A minus BI. Right? So, yung transpose, babaliktarin mo lang yung row at saka column number, pero pag sinabi kong conjugate transpose, ita-transpose nyo yung matrix, pagka-transpose nyo, i-conjugate nyo lahat ng mga entries. Okay? Kay MATLAB, ang syntax ng A conjugate or ng A conjugate transpose ay matrix A tapos apostrophe. Okay, so yan yung syntax kay MATLAB. Pero kung transpose lang naman, yung gusto mong kunin, kailangan A dot apostrophe. So yun yung pinagkaiba ng dalawang operations. Pero hindi tayo naging particular with this last time because kung real lang naman yung laman ng mga n nung matrix mo, yung A transpose ay nagiging equal lang sa conjugate transpose. Kasi ang conjugate ng real number ay sarili niya. Okay? So with those preliminaries out of the way, we can define what is the Moore-Penrose Pseudoinverse, or tawagin na lang natin siyang pseudo-inverse for brevity. So when we say that the pseudo-inverse of a matrix A is the matrix A plus, okay, A plus yung notation sa pseudo-inverse, siya yung matrix or siya yung kahit anong matrix na nakakasatisfy ng apat na properties na ito. Okay. Now, first, A times the pseudo-inverse times A is equal to A, meaning pagka ito, so parang ito, si A transpose A sort of acts as an identity. All right? Parang wala lang pag nag-multiply tayo to the right ng A transpose A. Pero yung, ng A, ng pseudo-inverse of A times A into the matrix A. So parang walang effect itong multiplier na ito. Or you can look at it the other way. Pwede mo naman tingnan yung A pseudo-inverse to be something that acts as an identity. But mind you, that identity might not be equal to the identity matrix at all. Okay? So kasi nga hindi pa natin alam kung paano nagwo-work yung pseudo-inverse. Basta dapat masatisfy niya yung property 1. At the same time, it should satisfy property number 2. It should serve as a parang weak inverse ng dapat si A pseudo inverse o si A plus A will act as weak left inverse. Si A plus times A should act as a weak left inverse or left identity. So dapat ito mag-act as if it's the identity matrix, right? Tapos, dito naman, this just tells us na her mission, yung A times A plus, meaning siya ay symmetric with respect to the conjugate transpose. Ang conjugate transpose ng A plus ay dapat yung sarili niya, at ang conjugate transpose ng A plus A ay dapat yung sarili niya. So, that is parang, ayoko na magdagdag ng terms, pero ito dapat yung apat na properties na masatisfy ng pseudo-inverse. Well, this definition is handy in verifying whether a certain matrix is a pseudo-inverse of one matrix. Pero mahirap siyang gamitin para computein kung ano talaga yung pseudo-inverse ng isang matrix A. Binigay niya yung characteristics na kailangang masatisfy ng isang pseudo-inverse. Pero hindi niya tayo binigyan ng paraan paano mag-compute ng pseudo-inverse. Okay? So when I ask you to check whether a certain matrix is the pseudo-inverse or is a pseudo-inverse of another matrix, then you need to check all these 4 properties. Dapat masatisfy sila. And that's what I want you to do in exercises 9.1 to 9.3. Binigay ko yung matrix A. Nagsulat ako dyan ng mga posibleng pseudo-inverse nila. And in this exercise, para ma-verify nyo kung yung A plus nga ba ay isang pseudo-inverse ng matrix A, you just need to check if these four things are identities. Kung totoo lahat ng apat na yan. Pag may isang pumalya, hindi na siya pseudo-inverse. Okay? So, if you have nothing much to do habang nasa bus kayo pa uwi, pwede nyo ipag-multiply yung mga matrix na yan. Ano? Okay, but before we go to the exciting part of knowing how to compute the pseudo-inverse, at least for a certain class of matrices, tingnan muna natin itong magandang result. Kasi ang sabi ng Theorem 9.1, kapag merong actually, dalawang bagay yung sinasabi nito. Lahat ng matrix A ay merong pseudo-inverse. At ang pseudo-inverse na yon ay unique. So basically, the articles that I use to precede yung pseudo-inverse, pwede natin itong palitan ng the. Kasi unique lang pala yung matrix A plus na makakasatisfy ng lahat ng apat na ito for a specific matrix A. Ang maganda sa 9.1, it's an existence and uniqueness result. It tells us there exists a pseudo-inverse for any matrix. Kahit zero matrix pa yan, kahit rectangular pa yung matrix na yan, laging meron yung pseudo-inverse. Tapos yung pseudo-inverse na yon ay unique. Pero, okay, with that in mind, siguro ngayon pwede na nating tingnan paano nga ba mag-compute ng pseudo-inverse ng isang matrix. Tapos titingnan natin paano natin siya magagamit para mag-solve ng linear systems. But first, I have here a remark which tells us bakit natin siya masasabing isang generalization ng matrix inversion. It is a generalization because if the matrix A is invertible, ang pseudo-inverse niya ay yung inverse niya. So basically, parang dinigdag lang natin. Kung meron kang non-singular matrices, okay, meron na silang inverse, so it doesn't make sense to give another value for the pseudo-inverse. Kung may inverse na siya, yun din yung kanyang pseudo-inverse. Talagang ginawa lang natin ay define lang natin yung pseudo-inverse para dun sa mga non-invertible matrices. Okay? So yun yung usual concept ng generalization. Di natin gagalawin yung mga okay na matrices. Dadagdagan na lang natin yung mga i-define lang natin yung parang magsaserve as the inverse, yun nga yung tinatawag nating pseudo-inverse para dun sa mga non-singular, para dun sa mga singular matrices at para dun sa mga rectangular matrices. Okay? Now, paano mag-compute ng pseudo-inverse at least for easy matrices? Okay? Now, kapag yung A star A, so yung conjugate transpose ni A times A ay invertible, okay? Then ang pseudo-inverse ay equal dito. Okay? And this definition, this result is apparent na kailangan invertible talaga yung A conjugate times A. Kasi yung formula ng pseudo-inverse, kailangan natin yung inverse ng A conjugate times A. Kasi mo-multiply ko yon sa A conjugate. Okay? Now, you can prove this using the definition. So, assume mo na si A star A ay invertible. Dahil invertible si A star A, so nag-exist ito, yung factor sa left. Tapos kung nag-exist yan, edi mako-compute mo si A plus. Alright? Tapos itong A plus na to, itong expression na to para kay A plus, i-plug in nyo dito. Sa apat na yan. And you will see that you will get 4 identities. Dahil na-satisfy ni A plus as defined in Theorem 9.2, etong apat na equations na yan, so madali lang yung i-verify. Computational lang naman siya. Or using properties of the Moore-Penrose Pseudoinverse, pero hindi na natin siya gagawin sa klase. Hindi ko na yun ipapaprove. Okay, malalaman natin na si A plus ay isang pseudo-inverse. But thanks to Theorem 9.1, unique yung pseudo-inverse. So we are forced to really say that A plus is equal to this guy. Okay. Pero on the other hand, na si A star naman, yung invertible, then yung pseudo-inverse ay equal dito. Now, if A star A is invertible, A star is not necessarily invertible. So, pwedeng silang dalawa ay parehas invertible. Pag nangyari na silang dalawa ay naging invertible, ito ay magiging equal dito. Pero pwedeng isa lang sa kanilang dalawa yung invertible. So kung sino man yung invertible sa kanilang dalawa, yun yung gagamitin mo para computein yung Moore-Penrose pseudo-inverse. Okay? Posible rin naman na yung A star A ay hindi invertible at saka ito ay hindi rin invertible. Kung silang dalawa ay hindi invertible, merong ibang formula or ibang theorems na mag-hold na magsasabi sa atin kung paano i-compute yung Moore-Penrose pseudo-inverse. Pero medyo linear algebraic na to or numerical linear algebra na yung magte-take care ng pseudo-inverse na yon. So I will we will just consider these two cases. Ning isa sa dalawa na to ay invertible. All right? Now in exercise 9.4, I ask you na computein yung pseudo-inverse ng anim na matrices na ito. All right? Now what you can do is first check if AA star is invertible. Kung invertible siya, edi gamitin nyo itong formula na to ng pseudo-inverse. Kung hindi, then tingnan nyo naman yung A star A kung siya ay invertible. Kung siya ay invertible, ito yung gagamitin yung formula. Now usually, kasi pipili ka kung sino sa dalawang i-check mo kung invertible. Usually pwede mo pwede mo ka mag-prioritize kung sino yung unang pipiliin mo. Kasi usually nakadepende dun sa ordering ng multiplication yung size ng matrix na kailangan mong i-check kung invertible o hindi. Halimbawa, ito si A. Ano ba tong size ito? 3 by 2. So pag kinuha mo yung AA star, siya ay magiging 3 by 3. Pero pag kinuha mo yung A star A, siya ay 2 by 3 times 3 by 2. So ito ay 2 by 2. Mas madaling hanapan ng inverse yung 2 by 2 kesa dun sa 3 by 3. So kung ako, uunahin ko munang i-check kung invertible yung A star A. Kasi 2 by 2 lamang yon. So yun muna yung check ko. Lucky tayo kung siya ay invertible, then mas madali natin makakompute yung pseudo-inverse. Kung hindi siya invertible, then mapapuwersa tayo na pumunta dun sa 3 by 3 case. So pwede yung diskartehan ano yung gagamitin nyo para makompute yung pseudo-inverse. But at least sana mag-fall siya dito sa dalawang cases na ito. Okay? Questions so far? I hope everything is making sense. All right. So kung wala namang reactions or questions, then okay, alam na natin at least paano mag-compute ng pseudo-inverse para sa ilang mga matrices. Ang tanong, paano natin siya gagamitin para mag-solve ng isang system of equation na either singular or rectangular. Okay? So kung ang isang system mo ay consistent, so doon ka lang makakahanap ng solutions kay AX equals B. Ang system lamang ay hindi unique yung solution. Actually, there will be infinitely many solutions to a consistent equation such as that in 9.2. So kung meron kang isang solution, tapos yung system ay overdetermined o underdetermined siya, so ibig sabihin there would be an infinity of solutions. It can be shown that any solution X will be of this form for any vector W of the correct dimension. Okay? So kung consistency 9.2, then kahit anong solution in 9.2 can be written with the aid of the pseudo-inverse of the matrix A. In particular, any solution X could be written as pseudo-inverse of A times the right-hand side vector plus the identity matrix of the right size minus A pseudo-inverse times A times any vector W of the right dimension. Okay? So kung si matrix A mo, hindi ko pala ito nabanggit kanina, ay M by N, si pseudo-inverse ay laging N by M. Okay, so parang ano siya, kasay siya nung transpose ni A. Tapos, so ang product na A transpose A will be N by N. So this guy should be an N by N matrix. So basically, this entire expression here should be N by N. Tapos halimbawa so ito ay N by M. So si B dapat ay M by 1. So ibig sabihin si W ay, ano dapat si W? si W dapat ay n by 1. Okay. So kahit ano pang n by 1 vector W ang i-plug in mo rito ay isang solution kung consistent yung AX equals B. So no fancy thing there, but here you see the utility of the pseudo inverse. It gives us the class of all solutions to the consistent over or underdetermined linear system. Okay, hindi ko na siya ipo-prove just for our appreciation. So tingnan na, yeah, just believe that this formula is true. You can consult any numerical linear algebra book for the proof, but actually yung proof ay pwedeng gawin using using what? Using the properties of the pseudo inverse lamang. So kaya lang hindi ko na present yung properties ng pseudo inverse kasi haba yung discussion. Now, kapag ka si A ay invertible, makita nyo nagwo-work pa rin yung equation 9.3. Kasi kung si A ay invertible, ibig sabihin si A pseudo inverse ay equal sa A inverse. Kung si A pseudo inverse ay equal sa A inverse, then this guy is the identity matrix. So tapos magkakaroon ka dito ng identity matrix minus identity matrix. So this guy will be the zero matrix. Kung siya ay zero matrix times any matrix W, that will still be the zero vector. Tapos this will be A inverse B plus the zero vector. This will just be A inverse B, which we know to be the unique solution of a non-singular equation AX equals B. All right. So the hold pa rin, general result yung 9.3. Nag-hold siya sa kahit anong consistent system. Consistent system na unique yung solution o consistent system na may infinitely many solutions. But that is not our main concern here. Mas exciting kasing mag-solve ng mga systems na inconsistent. Okay? Pero para masabi natin, what does it take for a vector to be a solution of an inconsistent system? Kasi ang problema rito, si X ay solution kung nasa-satisfy niya yung equation na yan. Pero kung walang X na nakaka-satisfy ng equation na yan, sino yung itatrato natin to be solutions to 9.2? Or what are the best vectors that we can call solutions, quote unquote, for AX equals B para sa mga inconsistent systems? And usually, ang kino-consider natin para dun sa na magiging solution ng isang inconsistent system ay yung vector na makakapagbigay ng pinakamababang residual. Right? Or that's what I called here the residual minimizer. Ibig sabihin, gusto nating makuha yung next best thing, the possible best next thing to a solution. All right? Gusto natin maliit yung norm ng AX star minus B. Of course, if your system is consistent, then this norm will be equal to 0 kasi yung AX ay magiging equal talaga kay B. So yung AX minus B ay magiging 0 vector. Ang norm ng 0 vector ay 0. Pero kung walang solution yung equation AX equals B, ang itatrato na lang natin to be a solution would be the vector X star that minimizes this norm. Yung may pinakamaliit na error or yung kayang palapitin yung AX star mula kay B. All right? And this is reliant on your choice of the norm. Okay? Kapag ang pinili mong norm ay L2 norm, the Moore-Penrose Pseudoinverse can give us the solution. All right? So kaya nating makuha yung minimizer ng residual na to kung ang gagamitin natin ay L2 norm. Right? At ang pagko-compute nun, kaya nating gamitin yung Moore-Penrose Pseudoinverse. So in particular here, I say that the solution to the inconsistent system AX equals B, insofar as minimizing the L2 norm of the residual is concerned, is given in 9.4. Okay, so ang best solution with respect to the L2 norm of the residual ay si A pseudo inverse times B. So parang napalitan lang yung A inverse by the pseudo inverse kasi nga hindi nag-exist yung inverse. So kaya napakaganda ng pagkaka-define ni Moore ni Penrose sa Kanibian Homer ng pseudo inverse. Kasi talagang it runs in parallel with the concept of the inverse of a matrix. So ito nga lang, makukuha natin yung pinakamagandang vector insofar as the L2 norm is concerned. So kapag ito yung kinuha mong solution, quote-unquote, dun sa ating equation, ito na yung may pinakamaliit na L2 o Euclidean error. Okay? And remember, the L2 norm of a vector is just, remember, kapag meron kang vector x, ang L2 norm niya lamang ay square root ng x1 squared plus x2 squared plus xn squared. Lagyan mo ng absolute value para kung complex number yung mga entries ni x. Pero this basically is the sum of the squares, all right? So kaya ang tawag dun sa solution na nakukuha natin using the Moore-Penrose Pseudoinverse, or the solution that minimizes the L2 norm of this residual, ang tawag natin sa kanila ay yung least square solution. Because this will give us the solution that minimizes the sum of the squares of the components of the error vector. Kaya ang tawag ay least square solution. Ito rin yung same least square solution na nakikita nyo mula dun sa, saan nyo nga ba ito ginamit? Sa regression? O ginamit din natin to yata sa 174 when we talk about the best fit or curve fitting, the least squares fit for a certain function. So ito yung tatawagin natin as the least square solution para sa isang inconsistent linear system. And I guess I need to borrow around 5 more minutes para matapos at least yung examples dito. All right, I hope you don't mind. Hold on, guys. All right, now let's see the Moore-Penrose pseudo-inverse in action. Let's consider example 9.1. So sa example 9.1, meron akong linear system AX equals B. Tapos si A ay 4 by 3. Tapos si B ay 4 by 1. So basically, I'm looking for a 3 by 1 vector that will solve AX equals B. But unfortunately, AX equals B is inconsistent, meaning it has no exact solution X. Tatawagin ko yung X na nakakasatisfy nito to be the exact solution, all right? Para lang ma-differentiate siya dun sa least square solution. So, pwede tayo mag-define ng iba't ibang methods para kung paano kumuha ng solution na may maliit na norm, okay? Na may maliit na residual norm para sa AX star minus B. One way to do this ay yung tinatawag na householder QR factorization. So ito isa tong matrix factorization method, which unfortunately we didn't have time to talk about. All right, so isa siyang method na gumagamit ng Gram-Schmidt orthogonalization process. I don't know if you have heard of it in linear algebra, pero gumagamit siya ng Gram-Schmidt process, pero householder variant para ma-decompose yung matrix A as a product of a unitary matrix Q and I think a lower or an upper triangular matrix R. Pag nirun nyo yung algorithm na yon, ang makukuha natin na solution ay si X sub H. Okay? Tapos pag titingnan ko, gaano kaganda itong gaano kagandang solution, all right? Quote unquote si X sub H. So para malaman ko kung maganda si X sub H na solution, ko-computing ko yung AXH, tas i-compare ko to kay B. Alright? So gusto natin ito dapat malapit kay B kasi nga alam na natin na walang solution, so it's impossible for AXH to be equal to B exactly. Kaya lang, ang gusto natin makita, ano yung pinakamagandang X na makukuha natin? Or what is the best X insofar as making AX very, very close to B? Now, apparently, this is not a good choice for the solution X because if we multiply A to XH, ito yung makukuha kong vector. But remember, the right-hand side vector is 2, 4, 6, 1. 2, 4, 6, 1. Yan nakuha ko ay 3, 3, 3.5, and 3.5. Parang visually, mukhang ang layo nung nakuha kong product mula kay B. Alright? And if you will compute the relative error, you will see that this norm or this quotient here is around 0.5. So meaning meron tayong above 50% na residual error, residual L2 norm. Pero yeah, so we can take a look at ano pa kaya yung pwedeng maging solution dito. Sino yung pinakamagandang pwede nating kunin as a solution? Well, our discussions earlier told us na ang pinakamagandang solution insofar as the L2 norm is concerned ay yung pseudo-inverse. So basically, we will compute A plus times B. Ito yung pinakamagandang solution with respect to the L2 norm. So let's do that. Let's see how good we can get to the vector B, all right? So compute natin yung A plus or yung pseudo-inverse. Remember yung pseudo-inverse na compute natin using the inverse of A star A or the inverse of A star. Dito ang ginamit ko ay si A star A. Kinompute ko si A star A. Ito yung nakuha ko. Alright, na matrix. Tapos, this one is invertible. Okay? Kasi yung determinant nito ay non-zero. So, siya ay invertible. Ang inverse niya ay actually ito. Pinakompute ko yan kay MATLAB. Pero exact naman ito kasi luckily, rational pa rin naman yung entries ng inverse na to. Tapos, computing ko yung pseudo-inverse dahil ito ay invertible. So, ibig sabihin, pwede kong computein si A pseudo-inverse using this formula. And if I do so, I'll get this matrix as the pseudo-inverse. And if I multiply this by B, I'll get this as my X star. And we are guaranteed that this X star is the best thing that we can get next to a solution with respect to the L2 norm of the residual. Ito na yung pinakamagandang pwede nating magawa with respect to the Euclidean norm. Kaya lang, unfortunately, when we compute for the relative error, it's still huge. It's 46%. Okay? Na malaki pa rin. Pero ang sinasabi nito, ito na yung pinakamaganda na makukuha natin. So there's no hope into getting AX very, very close to B. Kasi the best that we can do is within 46% error. Alright? Now, mukhang hindi siya nakakatulong. Actually, ang problema rito ay wala sa closure ng range ni A si B. Pero I don't want to talk about that. Kailangan nyo na ng 155 at saka 120 to understand those terminologies. But essentially, believe me that this is really the best we can do for that problem. Pero hindi naman ganun laging ka-useless yung nakukuha nating solution mula sa pseudo-inverse. Take, for instance, example 9.2. So in example 9.2, we have here a 3x2 matrix or 3x2 coefficient matrix, and we have a 3x1 right-hand side vector. So meaning we're looking for a 2x1 solution vector. Okay? So dahil ito ay rectangular, so i-diretso na natin, compute na natin yung pseudo-inverse. Now, ulitin ko yung pagko-compute ng pseudo-inverse. So titignan ko kung invertible yung A star A. Pero one way kung paano na-realize yung pagkakaroon ng pseudo-inverse ay yung solution na pinakita ko sa example 9.2. Nagsimula tayo sa AX equals B. Tapos dahil may gut feel naman ako na si A star A ay invertible. So ang gagawin ko, mula kay AX equals B, magmumultiply ako to the left both sides ng A conjugate. So nagmultiply ako ng A conjugate sa kaliwa ng mga entities dun sa ating equation. So we get this, and this is what we call the normal equation. Okay? Pag nagmultiply ka ng conjugate transpose sa kaliwa ng parehas na side ng isang matrix, na makukuha mo ay yung normal equation. Tapos dahil alam natin na si A star A ay invertible, we can multiply both sides to the left by A star A inverse. And that's what I did here. Ito, minultiply ko to dito. So kaya ako nakuha yung left side. Ito, minultiply ko dun sa kanan, pero sa kaliwa. Pero ang A star A inverse times A star A will just be the identity matrix. That's why nagsolo na si X dun sa sumunod na line ng equation. And look at this. This is exactly how we defined our pseudo-inverse. So this is one way how the pseudo-inverse was defined, okay, or paano siya na-discover, at least for A star A being invertible. So kaya naisip ng mga tao na, okay, pag nag-normal equation pala ako, tapos nangyari na yung bagong coefficient matrix ay invertible, eto na lang kaya yung tawagin ko na pseudo-inverse. All right? Which is in line with the theory, the formal theory that Penrose, Moore, and Bienhammer developed. All right? Tapos pag kinompute niyo yan, kinompute niyo yung A star A inverse times A star, tapos minultiply niyo dun sa right-hand side vector B, what we'll get is this two vector 1, 1. Tapos sige, maganda ba itong solution na nakuha ko? Maganda ba yung 1, 1 with respect to the L2 norm? Well, if you multiply 1, 1 to our coefficient matrix kanina, what you'll get is this guy, which is exactly the vector B. All right? So ibig sabihin, nakakuha tayo ng exact solution. This is not just simply the least square solution. It is also an exact solution. Kasi yung AX star ay exactong equal kay B. And we know that this is the best case scenario because the L2 norm then of AX star minus B will be equal to the minimum possible value, which is 0. Tapos titingnan ba natin, okay, so meron tayong solution, consistent yung ating overdetermined to, no? Kasi tatlo yung equations, dalawa lang yung degrees of freedom. So itong overdetermined system natin ay consistent. Meron siyang solution. Next question, meron pa bang mga solutions? Well, a quick check will tell us na, okay, computing ko yung A star A, kaya lang pag kinompute ko yung A pseudo inverse times A, magiging identity matrix na yon. Tapos babalik ako sa equation 9.3. Kasi yung equation 9.3 ang nagsabi sa atin na kung merong solution ng isang over or underdetermined system, lagi siyang papatak sa ganitong itsura. Okay? Pero, yung A star A, for our example, became the identity matrix. Dahil identity matrix na yan, I minus I, this will become the zero matrix times any vector W that will just be equal to the zero vector of the right size. So that means X will be just equal to A pseudo inverse B. Pero sabi natin yung pseudo inverse ay unique. So yung A pseudo inverse times B ay unique. So ibig sabihin, unique yung solution X natin para sa example 9.2. So wala nang ibang solution kundi si 1, 1. All right? Now, I still have here some examples, but I'm running out of time. So I'll just leave example 9.3 as a reading assignment for you guys. And then let's see kung makakapag-klase pa tayo on Friday. The worst case na mag-declare ng walang klase sa Friday, I will just make a recording. But if you guys have nothing special or nothing important to do on Wednesday at on Friday, kung mag-declare ng walang pasok tapos wala kayong gagawin, you can join me in the recording of the lecture. All right? 12 to 1 ko rin siya gagawin. So may link na naman dun sa ating Canvas page. Pero kung walang declaration ng suspension ng synchronous classes on Friday, I'll be meeting you live on Friday. Okay? Okay ba yun? So before we leave, any questions? Parang masyadong napabilis yung discussion today. But do you guys have any questions? Pahabol na lang. May shortcut to kay MATLAB kasi. So kay MATLAB, kapag ka meron kang system AX equals B, A ay rectangular, siya ay M by N. Tapos, si B ay M by 1. Pwede mong ipakompute yung least square solution right away kay MATLAB using a single line of code. Okay? So, pwede mong i-type si X ay equal kay A backslash B. Okay? Si A backslash B, actually, pwede mo itong gamitin kahit square si A or kahit si A ay non-singular, kahit siya ay singular or non-singular, it doesn't matter. For any matrix A, you can ask MATLAB to do this. All right? So kung si A ay invertible, ito ay kinocompute ni MATLAB to be A inverse B. Bibigyan niya yung unique solution. Pero kung si A ay hindi invertible, ito ay kukompute ni MATLAB as A pseudo inverse times B. So in either case, A backslash B will give us the least square solution for the system AX equals B. Okay? So kung gusto nyo mag-verify ng mga examples, pwede nyo pagawa kay MATLAB yung A backslash B. Actually, pag nag-compute ka ng, actually, ito yung suggested ni MATLAB. Pag nagsosolve ka ng linear system, kahit anong linear system yan, consistent, inconsistent, or whatnot, ito yung suggested ni MATLAB na gawin kesa kay X equals inverse of A times B. Kasi masyadong mahal yung pagko-compute ng inverse ni A. Usually, mas madaling mag-compute ng pseudo-inverse kesa sa inverse mismo ni A. That's why MATLAB prefers nang iutos mo na lang sa kanya ay A pseudo-inverse B kesa kay inverse of A times B. Because anyway, if A is invertible, then this guy will be equal to this guy. So wala rin naman problema. Mas mabilis niya nga lang masosolve yung A pseudo-inverse times B. Pero mas computational side na to. So yeah. Usually pag nagsosolve ako sa malaking code, ito yung ginagawa ko. One possible reason is because, hindi, wag na lang kasi hahaba yung discussion. All right, other questions? Clarifications? Totoo? Wala? Okay, so if there are none, so I hope you guys pick up something today. Medyo hindi formal yung discussion. These are just my concluding thoughts for the section. Though this will not come up in any of the lab exercises, pero posibleng magtanong ako about the pseudo-inverse and about the L-curve, which we will discuss on Friday or on the assigned recording to you. Tapos kasama siya sa problem set number 2. I-insert ko siya either on the first part or on the third part. Okay? So I think that's fine. If there are no questions, then thank you guys for joining me today. Tapos, bahala na. Let's see each other again either on Friday or Monday or pwede rin namang Wednesday next week. Wala pala sa Monday, no? Wait. Declared na ba na non-working holiday ang election day? Apparently hindi pala codified na holiday ang election sa atin, no? Parang all my life akala ko ay nakabatas na holiday ang election. Kailangan pa pala ng proclamation from Malacanang about the elections being a national holiday, a special non-working holiday. Pero since wala naman tayong lab extra on Monday, so wag na lang tayo magklase sa Monday to give you more time to vote, all right? So wala na lang klase sa lab on Monday, tapos kita-kits na lang tayo sa lecture ulit sa Wednesday. And hopefully on Wednesday, I will start the discussion about ordinary differential equations, all right? So until then, guys, keep safe and bumoto tayo, ha? Bye-bye, guys.